Alright, so here we are, final topic of the week. You might be thinking, final time I have to deal with equilibrium? And you're half right, because the next chapter we're doing thermodynamics. But at the end of that, it ties into equilibrium. And then after that we do electrochemistry. You're like, oh, okay. And at the end of that, it ties into equilibrium. So you're not totally done. So, if you're like, how does electrochemistry tie into equilibrium? Well, guess what happens when you have a dead battery? It's at equilibrium. Alright? You have to push it off equilibrium and then get work out of it as it returns. Alright? Anyway, let's talk about coupled equilibria. So, I've been hinting around this. I've given examples and been like, that's coupled equilibria. We'll talk about it later. So here we are. We are at that point now. And so what this is when we have multiple equilibrium processes. And they can be connected together. So sometimes you have multiple equilibrium and they're totally disconnected. They're not a couple. So how would they be connected? What would connect them together? So they can be, but how, right? What could do that? And the answer is by having a chemical species in common. So if you have something that shows up in two equilibrium processes, then the equilibria are connected. So we've actually seen this repeatedly. It's just kind of been silently there the whole time. Why does adding acid, even a weak acid, cause the amount of OH minus to decrease? And the answer is coupled equilibria. So, you have this relationship between H plus and OH minus. If H plus went up, OH minus went down. So if we put a weak acid in, you'd have this exchange between the acid and its conjugate base. That would create more H plus in solution, or H3O plus. And then that would affect the KW equilibrium, and OH minus would go down. So, those were coupled equilibria. It was just there the whole, silently the whole time. And this is also known as a common ion effect, or another example of the common ion effect. So the common ion effect will also occur in buffers, stuff like that. So, let's build on an example we talked about in the last video. Let's talk some more about the solubility of AlOH3, aluminum hydroxide. But let's talk about this in terms of being in an acidic solution. Why would an acidic solution affect the solubility of aluminum hydroxide? So remember, it's not very soluble, right? It was very, very, very little bit that would dissolve. Under the old rules, insoluble under the new rules, tiny little bit, nanomolar solution. Well, if we look at our KSP expression, or solubility dissociation equation, there we go. I'm getting tripped up on the vocabulary now. And again, this is exactly what we saw in the last video. Sorry, my phone kept buzzing. Alright, so this had a KSP value. Well, why would an acidic solution affect this? Well, there's another equilibrium going on. This is in water, right? So there's also KW, and we can flip and triple it. You'll see what I mean in a second. And so I'm going to put these on the reactant side. Okay. And so there's a common ion between them, hydroxide. So they're coupled. So if this starts to dissolve, it will react with the H3O plus and make water, which is going to pull this further right, which is going to increase its solubility, okay, because we have a high concentration of this. And so what's K for the second expression? Well, it's just KW, so 10 to the minus 14. Now if I add them up, I get to cross out any stuff that's in common. And so I get the following. That's solid, by the way. That's a key detail. I want to make sure you have that in there. And then, okay, I got liquid there. All right. So we get that, and we get 6 waters. Okay? So we have a new combined equilibrium expression. So that's why I tripled it and flipped it, so I could cancel the OHs. Alright? And so this actually isn't KW, because I flipped it, it's 1 over KW, and then I tripled it, so it's cubed. So just like we would do with the reaction rate constants, we can do the same thing with the equilibrium constants. I might have talked about it with just the equilibrium, but anyway, we've talked about this before. So if I flip a reaction, the reactants become products, products become reactants, so the whole thing flips. If I triple it, it's cubed. I exponentiate it. If I were to double it, I would square it. Quadruple it, I put to the power 4, so on and so forth. This one I didn't mess with, so I just leave it as it is. And so for this combined expression, KEQ is going to equal the product of all this stuff up here. If I do 3 equations, I multiply all 3 of the individual K's by themselves. But there's only 2, so I go KSP times 1 over KW cubed. And so KSP, you'll remember from the last video, that was 4.5 times 10 to the minus 33. And then it'll be times 1 over 10 to the minus 14 cubed. And so you just punch it all up for the math, and you get 6.2 times 10 to the 15. Does that make sense? I mean, does that number make sense? Maybe the process doesn't. You need to revisit some stuff, but so I think there's the physical explanation. Hopefully that made sense for why this system would be pulled right, why this would become more soluble, and does this value of K, does it work with that explanation? So we have a large value here. What does that mean? That means there's going to be a lot of aluminum ion in solution. Okay? So, yeah, that makes sense. It heavily favors products because it's a large value, which means more soluble. Okay? So, that's the first example we're going to talk about. And I think that makes sense. Like we can talk about the chemical explanation, we can tie acid-base chemistry into this, and we can understand what happened here, and we can see that, you know, we do some tricks with the math, and we can model that. Now, hopefully it makes sense that acid would cause that to be more soluble. Now prepare to be blown away. Oh yeah. So again, let me back up here before I get started. So Le Chatelier's principle explained everything. We remove this, we shift right to compensate, to have equilibrium, which means we're more soluble. That's Le Chatelier's principle in action. We're perturbing our system, and it's adjusting. Now, what if I told you this? Adding more hydroxide makes aluminum hydroxide more soluble. What? That doesn't make any... The acid-base stuff does not explain this. That makes no sense, right? And you're correct in thinking that. There's a missing piece. And that is the Al OH4 what would it be? It would be minus, excuse me. Be an anion, minus, just minus 1, complex ion. And now maybe you're starting to see how the pieces fit together. So again, we have a coupled equilibrium system. We still have the solubility expression here, or equation. Okay. But we also have the formation of our complex ion. So what goes into forming that complex ion? Well, you're going to have your aluminum, 3+, and you're going to have, I don't know, about 4 hydroxides. Okay, and so this has a value for KSP, and this is just our expression for KF. No fancy math needed. And we can total them up. So the 4 becomes a 1 because it cancels with all 3 of those. My aluminum cancels, so the ion doesn't factor in. And so what we get is aluminum hydroxide plus a hydroxide ion goes into equilibrium to give us our complex ion. Which is going to give us a value for KQ. Which, by the way, this is an interesting expression, you know. It'll be the concentration of the complex ion over the concentration of hydroxide. And so, if we, those are the only 2 variables, right? It's not about the aluminum at all, which is interesting. But anyway, what does this equal numerically? It'll just be KSP times KF. And let's see, so we know the value for KSP, we've talked about it before. It is 4.5 times 10 to the minus 33, so it was a very small number. It wasn't very soluble, right? KF is 1.1 times 10 to the 33. Just kind of a coincidence that the powers of 10 are the same. And so it comes out to be 5.0. No power of 10 at all needed. Okay? And so what does that mean? Well, we went from a really small number to, a moderate one. It's above 1, so this is definitely going to be more favored than this. That means increased solubility. So there's lots of different chemistry that can cause some maybe unexpected effects. So if you forget about complex ions, this would make no sense. Acid-base chemistry does not explain it at all. But once you remember, like, oh, or you're told that there's a complex ion, you go, oh, and then you can just jam through, and So my next question is, which one's better for dissolving aluminum hydroxide? Adding base or adding acid? Acid. The answer is acid. So the base works, which is weird, but the acid's going to be more effective if you're really trying to dissolve a lot of it, because the K value is much, much larger. Okay, this is like you got $5 in the bank account. This is like you have all the world's money, right? Like, let's see, you would have $1,000,000 billion. That's 10 to the 15. $1,000,000 billion. All right. So, versus 5. Yeah, you've got who's on the? Is it Abraham Lincoln on the 5, right? I wasn't kidding earlier. I was like, yeah, you use coin purses and you buy stuff, and now you use cards. Like, I never have cash. It's like never have cash on me. If I do, it always seems to disappear from my wallet, and then my wife has some new thing she bought at the store. So I don't know. Which is, I mean, she has all the same cards I do. I don't know why she wants to take my cash. But anyway, she wants to, like, provide cash tips to people or stuff. You just fill out the little slip on the bottom, which probably is, maybe gets the money to them. Who knows? Anyway, I hope it does. I mean, I'm not trying to be a jerk. Like, I hope it does. But anyway, so this is less soluble, but more soluble than just in a. So it turns out neutral pH is when this is going to be the least soluble. What an unexpected result. And so with these coupled equilibrium systems, we just do this trick. We can find the new K value, and we can compare it to the old expression for the solubility, or whatever we need to compare to say, like, is this more soluble or whatever, or maybe we just need the value. But again, Le Chatelier's principle can explain this. If I add enough hydroxide, this shows up in a significant amount. It's going to remove my aluminum ion, that's my common ion, as well as the hydroxide a little bit. But this will be the big one because it completely cancels. And so this system is going to shift right. So this is going to pull aluminum out of solution. This is going to shift right to replace it. Alright, so, and because it doesn't completely cancel the hydroxide, that's why you would have a less significant, but not as significant of effect as completely removing the hydroxide like you did in the other one when you added acid. Alright, so that'll do it this week, and that'll do it for our equilibrium specific chapters. Again, equilibrium is not going away, but it's not going to be at the forefront either. And so if you take organic chemistry, it's not going away either, because all of your reactions that you do in organic chemistry are equilibrium reactions. So you're always trying to drive equilibrium towards products, because that's what you want at the end of the day. You don't want stuff you start with, you want stuff that you end with. And so, if you think back to reaction yields, way back in the old stoichiometry days, I think either me or hopefully whoever you had for chemistry would mention, for Gen Chem 1, would mention that you never really have 100% yield. And the reason is actually because those reactions are equilibrium processes. Almost every reaction we do in a beaker is reversible. And so, you are driving towards products, but you never get 100%, plus losses and purifying and transferring and stuff. And so that's the key idea for organic chemistry too, because when you do a reaction, you're often doing a reaction. You make something, isolate, react it more, isolate it, react it more, so on and so forth, and then finally purify at the end. And, you might only have 40% yield or something. And that might be very good for the reaction you're doing. It might be very poor. It just depends on these processes and how much we can drive them towards products and how many losses along the way you might have. Alright, so that'll do it this week. As always, any questions, let me know. I'm happy to help. And I will say no more ice tables. So that's good, right? This is the last week of that. So you finally probably have mastered them, and then we get to move on to things like Gibbs free energy and the Nernst equation instead. So welcome to general chemistry, where each chapter is different than the last, except for these three in a row. All right. Anyway, let me know if you have questions. Otherwise, have a good week.